So my name is Amy Wang. This work is done by Huawei Canada, where I work in the Programming Languages and Compilers group. The title of the talk is Replayable Execution Optimized for Page Sharing for a Managed Runtime Environment. The co-authors are my colleagues, Rayson Ho and Peng Wu. So the motivation, function as a service, FaaS, is an emerging programming and application deployment paradigm. Many companies have FaaS services. For example, Amazon Lambda supports Java, C#, Python, and other languages. So is Huawei's function stage, supports Java, Python, Node.js, Go. How FaaS works is that an external cloud event will trigger the FaaS framework to deploy and to launch a user function or a Lambda. It's typically deployed using Linux container on computing resources. As you notice that a lot of the languages are managed runtime languages. So managed runtime FaaS frameworks suffer from two performance concerns. One is the memory footprint blow to host the runtime, and also the long initialization time to initialize the framework. So myself and my team were presented the challenge from our cloud business unit to look into these two problems. So in the Huawei context, I want to motivate the talk a little bit. So the FaaS framework in Huawei has a HTTP over TCP request proxy that is responsible for receiving HTTP requests, and in turn the proxy will route to a Unix domain server. It's built using open source frameworks. The Unix domain server, for instance, for Java is based on Netty. For JavaScript, it's based on Node.js HTTP module. For Python, it's based on Tornado. So we did an initial assessment of all the FaaS frameworks that Huawei offer. Here I present three managed runtime frameworks: Python, JavaScript, and Java. As you can see that the startup time for Python is about 102 milliseconds. But for Java, without app CDS, application class data sharing feature, which is a commercial feature from Oracle JVM, it's at 780 milliseconds. Because app CDS is a commercial feature, and if you were to use it, you need to pay license fee. So I present a number without, but in the paper and later on, there are numbers presented using app CDS. As you can see, the language runtimes takes up a lot of memory. You would ask, why would we care about 94 megabytes or 16 megabytes when there are gigabytes of memory running around? So one thing to remind everyone is that, well, actually, this is a statistic provided to us by the cloud Huawei operator that the 128 megabyte container is most popularly used. As you can see, if you apply for a 128 meg container, and 94 meg is doing pretty much nothing too much, just hosting the framework, that becomes a substantial proportion inside the 128 meg. Of course, different framework, different managed runtime languages have different considerations. For example, Python does not have a just-in-time compiler, whereas Java does. The memory management is different. We decided to focus our energy, although we do supply performance numbers for Python and JavaScript, but we focus most of our energy on Java. As you can see, Java has the most significant overhead in terms of startup time and memory usage. For the reason that JVM is complex. It has just-in-time compilers, probably not just one, C1, C2, there are two, garbage collector, thread management, all happening inside the JVM. So our approach to tackle these two problems stems from two observations. So first observation is that we realize application built on a complex framework exhibits pronounced intensive-deflated FaaS execution characteristics. So what does that mean? The memory usage at time t, for instance, at phase I is the framework initialization phase, and the memory rises fairly high. So the working data set rises. However, after the initialization phase, the application typically sits in an event loop listening to requests, and the working set drops significantly. So our observation is that it would be nice to be able to store away the private dirty memory to disk. The second observation is that the live data is very similar between applications that share a lot of common code base. For example, application built on top of the same framework, such as Spring Boot or Spring Cloud. So from these two observations, I'm going to explain the 3 key points that drive this work. So first key point is live but not in use data, as you can see from this graph, the blue box. Those are the anonymous memory. We'll store that to disk. And we like to on-demand page in the live data into memory. This is achieved via mmap. And we want to jumpstart a framework from time S where the framework has been initialized. With these 3 key points, we bring down the memory usage as well as we speed up the startup time. And we do this by doing checkpoint and restore at time S. And we restored using mmap. So from the context of JVM, you may ask, what can be stored to disk? So there is the dirty heap. So the non-working data set can be evicted. Data that is live but not in active use, you cannot just get rid of these data. They are live but just not actively used. Now with a backing store, it can be on-demand paged in. JVM work area, for instance, runtime state, the VM runtime state, such as pthread to Java thread mapping. These are important data but cannot be evicted. So now with checkpointing, it can be placed onto the disk. Class metadata, which includes bytecode, can also be evicted to disk. This is assuming that you have just-in-time compile the native code. So only the native code needs to be in memory to be executed. Class metadata and bytecode can be placed onto the disk. JIT work area, or just-in-time compiler working area, that was used to compile the JIT methods. For instance, compiler needs a lot of memory to do its optimization. This can be evicted to disk as well. So net of it, what needs to be in memory is really just the current working set and perhaps some of the JVM work areas, such as the method PDF counters. And a key point is the just-in-time compile code is now clean and can be shared. Just-in-time compile code is typically generated at runtime in the anonymous memory, which cannot be shared unless you go through extensive engineering effort to make them position independent and make them shareable. So in our method, JIT compile code is actually clean and shareable. So then you would ask, how do you identify a checkpoint location? Ideally, you want to checkpoint as late as possible to maximize the common code path, but you have to do it before the execution paths diverge. In this context, you want to do it before loading in the user FaaS function. We have tools to help identifying whether a workload is a good candidate for our optimization. We use the solve dirty page table entry method. By clearing the solve dirty bits, we make the pages read-only. If the process tries to read it, it will cause page faults. So between the 2 time points, we will clear the dirty bit in 1 time point and then read the solve dirty bits and present bits from the page map to calculate dirty pages. We can also use a process that you modify the application to fork off a child process, but put the child process in pause state and monitor the shared dirty bits. If you notice that in the valley state, you have small amount of dirtied memory, then the application is a good application candidate for replayable execution. Memory divergence can defeat the savings. As you can understand that a restore process, if it moves into a different memory phase where it decides to rewrite a large portion of its memory, then it can defeat the memory saving. This can happen when execution behavior changes and the JVM decides to deopt and then re-JIT again, and the JIT work area will be pulled right into the RSS. So we want to prevent the process from altering the common code base as much as possible. We did not have the luxury to modify OpenJDK at the point of this work. So to achieve this, we train or warm up the JVM so all the JIT code is generated before checkpointing. And we had to ensure the correctness of diverging execution paths after restore. For instance, when you launch two FaaS functions, they may have different environment variable settings. So we have to handle that carefully. This is a requirement. Different user launches their FaaS function under different environment variables. This can be tricky. Despite we update the process layout in terms of environment variables, JVM stubbornly caches environment variable onto its Java heap, and it became very difficult to search out the whole Java heap where JVM places its environment variables. So we had to overcome that to ensure correctness of diverging execution path. So to briefly go over the workload of Huawei FaaS framework, earlier I alluded to that we have a process router which is fronting the JVM. It's a proxy. It receives HTTP requests over TCP, and it filters out a lot of the invalid requests. So it's like a front line of safety. And JVM sits behind it, listening to Unix domain sockets and handling requests that way. So we had to we checkpoint the JVM in privileged container because we use CRIU, which requires usage of ptrace. So we need to be in a privileged container. This is done offline during build time. So that means when there is a revision of the framework code, you just need to do it once. However, to restore, this has to happen online when user request actually comes. And we have to do it as a non-root user in a non-privileged container. And a lot of the heavy engineering lies in making the restore work in a non-root user setting and a non-privileged container. Here it shows that the total RSS using the shared dirty and soft dirty tools, we determined that Huawei's Java FaaS framework is a good candidate for replayable execution. So I won't go through all the heavy engineering lifting that went behind the scenes. Notably, there are a few, so I'll just list them out here. We had to modify CRIU restore to use mmap instead of prev to benefit from the page sharing, as well as to mmap is significantly faster in that you don't have to prev copy the virtual pages into the address space. CRIU will fork a new process to restore the JVM, but we had to eliminate that. So what happens is that the CRIU process becomes the JVM. So that's also a significant change because we do not want people to feel that this new JVM that we created, which is truly CRIU in disguise, feels a bit different, like basically restoring, going to background, and the JVM process happens. If it doesn't feel like a regular JVM to our user. So that's why we did that. And we had to remove ptrace usage. As I said, non-privileged container, the Docker seccomf profile filters out ptrace calls. And we had to overcome the prohibited usage of PRCTL when restoring program break because we are non-root user inside the container. And we had to do some PID translation work because despite we update the glibc's caching of TID, PID, again, JVM stubbornly caches the PID on its heap. And we had no way of fishing it out where it is on the Java heap and update that. So we had to provide a PID translation mechanism. More heavy lifting, because this is actually production work, so we had to deploy this. We had to take into consideration of fairness of memory accounting. As you can see that we rely on page sharing. So according to C group, the first process that touches the page, which causes the page fault, will be accounted for that memory. So this is unfair for the first JVM launch user because subsequent ones can benefit from the page sharing at zero price, whereas the first user had to pay for it. So we had to overcome this by pinning the checkpoint file with mmap locked in memory ahead of time with Kubernetes daemon set mechanism. Again, OpenJDK 8 does not have dynamic heap resizing. So if we checkpoint, for instance, with a max heap of 128 meg, we had no way of resizing it at restore when the user suddenly decided to use a 1.5 gig container, which has a bigger max heap setting. So by that, we use JVM ballooning, so we can release the balloon to dynamically adjust the heap, which is a work that we have continued to do to appear on CloudCom 19. Okay, evaluation. We use Oracle Hotspot 64-bit server VM. And the baseline flags is a set of competitive flags that our serverless team has been using. This is for 128 meg container. It uses serial GC, which is fairly simple generational GC, and it disables tier compilation and sets the netty event loop flags, event loop threads to 4. And again, this is our hardware consideration environment, and we use this Ubuntu version 16 with Docker container. The experiments focus primarily on startup time and the JVM memory usage over a long term, serving thousands or hundreds of thousands of requests. So evaluation, the startup time, we provide the startup time for various FaaS managed runtime languages, including Python and JavaScript here. How do you measure startup time? The startup time is when a framework is properly started up and can listen and respond to a request. So we measure startup time from when the network gets started until, and we send a request to it, and the framework will respond with a reply. When that completes the loop, we say that the framework has been properly started up. So from here, we can see that we are able to bring down the startup time for Oracle JVM 780 millisecond with AppCDS 474 millisecond down to 54 because we restore at time S without executing from time 0 again. So that's a significant improvement on startup time. Similar improvement can be observed with Python and JavaScript. Because we train the JVM prior to checkpointing, the JVM is already executing JIT code, so it's able to respond to a request at 2 times the speed because native code is far more efficient than interpreter. Okay. For memory footprint, we gather the memory footprints for the 4 runs, which is Oracle JVM and Oracle JVM with AppCDS, which application cost data sharing. And we also compare with untrained JVM with no training, and we do checkpointing, as well as trained. So we notice, of course, the trained replayable JVM gives the best memory, which is this red line, the lowest red line. And we felt obliged to really dig into what is happening in this red line. Why does it still need 60 meg? We did a detailed analysis into it. What comprises of the 60 meg is really the transient garbages that's building up in the young generation. Despite we're sending HTTP requests and it's once and then it finishes, it's stateless, but it builds up transient garbages, and the GC only collects it when the garbage builds up to a certain threshold. And serial GC is a much simpler GC. It does not return the dirty pages back to the OS despite its dead data. So as you can see that the memory 35 meg roughly is consumed by transient garbages. And we also plotted the JIT activities. So when the JVM loads in the user FaaS function that it's never seen before, it will trigger JIT activities. Therefore, this bottom blue lines were the intensiveness of JIT activities. And we found when there's JITting happening, memory rises. This page describes that ReplayableJVM brings down the RSS overall, and it also enables more sharing. As you can see that the RSS over the private dirty pages are much wider. This is for multi-container runs. In conclusion, I leave you with this picture because this is where all the ideas came from. I explained that earlier. And finally, I want to say that the work is publicly available on Huawei's function stage. If you write your Lambda function and print out /proc smaps, you can see the ReplayableJVM at work. And it's free of charge. You can go online and try it. So that's all.
Hi, I'm Christian Dietrich from Leibniz University. Thank you for a nice talk. I wonder if you could compare your approach to where I have a JVM as a hot standby process and I fork my JVM from that, so that the operating system with the copy on write does all the heavy lifting of the sharing of pages.
Yeah, that's a good question. We thought about that. The only thing is when you fork off a child JVM, you need to recreate all the kernel states associated with that. For example, kernel states as in the threads, like you recreate all the thread state, the file system states, and that the mutexes and whatnot. That requires significant modification to the JVM, and we had no such luxury. So. Yeah, sorry. There.